Hello, everyone. It's always an honor to give a talk at a STOC conference. So today, there's a great deal of interest in computational thinking. Well, in 2006, Jeanette Wing wrote a very influential paper in which she said, computational thinking is a fundamental skill for everyone, not just for computer scientists. She went on to say that it's as important as the 3 R's to every child's education. Since she wrote this paper, a great deal of discussion has taken place on how computational thinking should fit into both computer science education and STEM education. About 10 years ago, Peter Denning asked me to write a paper for his ACM Ubiquity column on what I thought computational thinking was. And I defined it at that time as formulating problems using abstractions so their solutions can be represented as computational steps and algorithms. Since that time, the definition of computational thinking has broadened, but it has become a lot fuzzier. In my talk today, I'm just going to focus on its 2 key ingredients, abstractions and algorithms. So what is an abstraction? Well, it's a mathematical model with 2 components. It has a data model and operations for manipulating that data. And I'm going to call those operations the programming language of the abstraction. But in many cases, this programming language is not Turing complete. Let's take an example of a simple abstraction, the dictionary. Its data model is a universal set of elements and a subset. Its operations are insert an element, delete an element, and look up an element. Dictionaries are used in many applications in computer science, particularly in compilers, to implement the symbol table of a compiler. When used in a compiler, the universal set of elements are the character strings, and the subset is the set of valid variable names that the compiler has seen as it's processing a program. I think all of you are very familiar with a dictionary. In putting a talk together for the Turing Award, Jeff Ullman and I decided to create a taxonomy of abstractions that were useful in programming languages, compilers, and database systems. And we created a simple taxonomy with 4 categories: fundamental abstractions, abstract implementations, declarative abstractions, and computational abstractions. I'm going to say a few words about what we meant by each. The fundamental abstractions are those that you would study in a first course on data structures. They're standalone abstractions like a dictionary or a stack, or they can be abstractions that might be embedded in a general purpose programming language, but they're essentially classes and their methods, but without implementation. And so graphs and trees would be good examples of these kinds of fundamental abstractions. The abstract implementations are used to support fundamental abstractions. They're data structures such as hash tables or search trees. They admit of different instantiations at the machine level. So a hash table, for example, could be implemented in a random access model of computation or in secondary storage model. And these 2 implementations would have very different notions of what their running time was. The declarative abstractions are probably the most useful. They're high-level abstractions that specify what you want, but not how you do it. They need detailed implementations to be executable. They're very valuable because they make programming much easier, and they're not Turing complete. And I'll use 3 examples, actually 4 examples of declarative abstractions in this talk. 3 from compilers, regular expressions, context-free grammars, and flow graphs. And the 4th declarative abstraction I'll talk at the end are quantum circuits. The computational abstractions are abstractions that are very close to the machine level or can be directly translated to one. So the random access machine, the Turing complete programming languages are there, and then abstractions for computer-like things that are not conventional, Turing machines, Boolean circuits, and quantum circuits, when you look at them like Boolean circuits, would be a computational abstraction. Here is a diagram that tries to tie these concepts together. So if we have an abstraction, we can implement an abstraction in terms of other abstractions. So we talked about implementing the dictionary abstraction as a hash table, and the hash table itself is an abstraction. Or we could use the 3 operations of a dictionary, insert, delete, and lookup, and create an algorithm using the innate operations of the abstraction itself. But in order to obtain a running time, we need to compile those operations into something that's executable or can be made executable by going down the layers of abstractions and algorithms depicted in this diagram. And this will become clear as we go through the talk. So let's focus on a very concrete example, and let's look at the abstractions and algorithms that are used in programming language compilers. So let's open the lid of a compiler and peek inside to see what's inside. For all of you who've had a compiler's course, I'm sure you've seen this diagram. For 50 years, this has been the bedrock diagram of a compiler. It shows the compiler as a composition of phases. The first phase is called the lexical analyzer. It takes the source program and transforms it into an intermediate representation consisting of a stream of tokens. These tokens are fed to a syntax analyzer, or parser as it is often called, which then tries to impose a grammatical structure in the form of a syntax tree on the token stream. The syntax tree is passed to a semantic analyzer that checks to make sure that the program makes semantic sense. For example, checks to make sure that the types of the operands and operators match. It may make annotations on the syntax tree and pass the annotated syntax tree to an intermediate code generator. The intermediate code generator then transforms the syntax tree into an intermediate representation, which often is some kind of 3-address code. Optimizing compilers will have an extensive code optimization phase where they apply scores of transformations to the intermediate representation in an attempt to make it easier to generate better target code from the intermediate representation. After the code optimizer has done its job, it feeds the intermediate representation to a target code generator that produces the target program that we wanted. And all of these phases get coordinated by a symbol table that keeps track of information collected by the phases and used by the phases. Let's look at the phases in a little bit of detail, or some of the phases, and let's begin with the lexical analyzer. Regular expressions are often used as a declarative abstraction to specify the structure of tokens for lexical analysis. The data model for regular expressions using our definition of an abstraction just consists of sets of strings, and the operations of regular expressions are familiar union, concatenation, and Kleene star operator of regular expressions. But in order to use regular expressions in a lexical analyzer, we have to transform the regular expression into some kind of algorithm. And there are many different ways of transforming a regular expression into a pattern matcher that can be used in a lexical analyzer. In this slide, I've shown 3 common choices for implementing a regular expression pattern matcher. The most venerable of these is what's often called the McNaughton-Yamada-Thompson construction, and it yields an algorithm for matching regular expression patterns that runs in time that's proportional to the length of the regular expression times the length of the input string that's being processed. This is a very good algorithm for short regular expressions. And when I first joined Bell Labs, the Computing Science Research Center in 1967, after graduating from Princeton with Jeff Ullman, I might mention, Thompson had also just joined at the same time, and he and Dennis Ritchie created the Unix operating system. And one of the first programs that Thompson put on his Unix operating system was a regular expression pattern matching program called grep. Grep, as many of you I'm sure know, stands for Global Regular Expression Print. It was a command borrowed from a QED text editor that Thompson had implemented earlier. When I came to Bell Labs, I liked doing crossword puzzles. I liked using the grep program, but I missed the fact that it didn't have all of Kleene's regular expression operators in it, particularly union. So I constructed an extended version of grep that I called egrep that included parentheses for grouping and added the union operator to Thompson's concatenation and Kleene star operators. And I created an implementation of egrep, first using a deterministic finite automaton. I created a non-deterministic finite automaton from the regular expression, converted it to a DFA using the subsets construction, and then simulated the DFA in as fast a manner as I could. And this yielded an algorithm whose running time was exponential in the size of the regular expression. But once you had constructed it, the regular expression, the deterministic finite automaton, could be made to run very fast. And in fact, I created an implementation for the first version of egrep that had 3 machine instructions per input character to simulate the behavior of the DFA on the input string. Things were going along quite well, but then my boss, Doug McElroy, he's the guy who invented pipes on Unix and also recursive macros, or co-invented recursive macros for programming languages. He liked using egrep because it had the union operator, and he once constructed a calendar program which would allow a user to specify dates in a variety of formats. As you're well aware, you could write June 25th as 625 or in a variety of other ways. So he had these very long regular expressions with lots of unions in them. And then he discovered that because I constructed a DFA from the regular expression, egrep spent a lot of time constructing this huge deterministic finite automaton. But once egrep created it, it processed the input very quickly. But this was a little bit like building a Boeing 747 to go across the street. You spend almost all of your time building the airplane and very little time flying it. So what I did was I created a second version of egrep where I wouldn't produce a state transition for the deterministic finite automaton unless it was needed. So this yielded an algorithm whose observed running time was linear in the size of the regular expression plus the size of the input string. To this day, I don't know whether this can be achieved in the worst case from a theoretical point of view. So I leave this as an interesting open question. If you have a solution to it, please let me know. But the upshot of this is that matching regular expressions became almost instantaneous. And this made my boss very happy. And it's good to have a happy boss. Let's go back to the lexical analyzer. Michael Lesk and Eric Schmidt created a lexical analyzer generator using regular expressions as the abstraction. Eric Schmidt was a summer intern, and he took my dynamic regular expression pattern matching algorithm and incorporated it into Michael Lesk's lexical analyzer generator. So you could create a lexical analyzer very simply by writing a lex specification, then ran it through the lex compiler, and it would produce the lexical analyzer for the front end of a compiler that transformed the source program into a token stream. And let me just illustrate how this went. So here is a very, very simple example of a lex specification for a token consisting of an integer number. We see regular definitions using regular expressions for specifying a number as a sequence of one or more digits. And then after the regular definitions are translation rules. And here's just one translation rule that says, if the lexical analyzer recognizes a number in the input string, it executes a semantic action of installing that sequence of digits into a symbol table and returning the token num for the syntax analyzer. So Lex became very popular for creating not only lexical analyzers, but all sorts of language processors. But let me show how it was used in connection with another programming language component generator, namely a parser generator for creating syntax analyzers. Abstractions for syntax analyzers include context-free grammars. By the way, context-free grammars are very old. There was a Sanskrit scholar by the name of Panini, who in the 4th generation BC used context-free grammars to create a grammar for Sanskrit. Of course, much more recently, context-free grammars have been used in the specification of programming languages. They're sometimes called BNF, or Backus-Naur form, by people who write programming language specifications. And they were also made very popular by Noam Chomsky in the Chomsky hierarchy of grammars. Don Knuth came along and in the mid-60s wrote an influential paper on LRK grammars. The LR stands for left or right, and the K means that you can deterministically parse the grammar with K symbol look ahead. Steve Johnson, Jeff Ullman, and I looked at Knuth's LR grammars and LR parsers. And we very quickly discovered that the parsers that you would construct using Knuth's algorithm as it was currently or constituted at that time in Knuth's paper would yield humongous parsers. And also writing even just an LR1 grammar required a lot of knowledge about grammars. So what Steve Johnson, Jeff Ullman, and I did was we took the framework of shift-reduced parsing and made it applicable to parse ambiguous context-free grammars. And just to illustrate the idea here, if we see an arithmetic expression as 1 + 2 × 3, we can have a choice of reducing 1 + 2 into an expression and then multiplying it by 3, or we can choose to multiply the 2 and 3 together and then add the result to 1. Specifying arithmetic expressions as a sequence of numbers separated by operators is a very easy way to write a grammar for it. And if we distinguished the associativity and precedence levels of the operators separately, we discovered that you can write very simple grammars for programming languages and make them efficiently parsable. So Steve Johnson took this idea and created a syntax analyzer generator. It would take a specification of a syntax analyzer, which got to be known as a YAC specification. And when you compiled it, you'd automatically get a syntax analyzer that you can plug into the compiler framework. I might mention that it was Jeff Ullman who coined the name YAC. He meant it to stand for yet another compiler. So the combination of Lex and YAC turned out to be a real winner. Let's construct a desk calculator using Lex and YAC. So this slide shows the specification, a YAC specification for a very simple desk calculator using the binary operators plus and times and tokens for integers. And we're using num as the ID for an integer token. The translation rules are really a context-free grammar with semantic actions attached to them. And when you look at the part of the grammar here for expressions, you see that the grammar is ambiguous, but in conjunction with the associativity and precedence rules specified in the declaration section, the grammar becomes unambiguous. And YAC and Lex had the nice combination that they could be used together to create the front end of a compiler. So if you compiled the lex specification and this yak specification together, you would have a working desk calculator. What this illustrates is with the combination of lex and yak, constructing the front end of a compiler for a programming language became a very easy job. I'll say a little bit more about this shortly. For the third abstraction involving compilers, let's skip over to the code optimization phase of a compiler. And for certain optimizations like constant folding or detecting common sub-expressions, an abstraction involving reaching definitions is used. And we'll say that a 3-address statement, the code optimizer now is processing the intermediate representation in the compiler. So if we have a 3-address statement, say of the form u is assigned v plus w, we say that this statement generates a definition of the variable u. And we say that a definition of the variable u from this statement S reaches a statement T if there's an execution path in the intermediate representation from S to T where u is not redefined. To compute these reaching definitions, it's nice to create an abstraction called a flow graph that identifies the flow of control within the intermediate representation. And we can represent the flow graph as a directed graph where the nodes represent basic blocks. Excuse me. And a basic block is just a sequence of 3-address code with no branches in the middle. So if control flow goes to the top of the basic block, it exits at the bottom of the basic block. The reaching definitions problem can be formulated as what definitions of each variable reach what program points. And as I mentioned, reaching definitions are useful for implementing a variety of different code optimizations. Constant propagation and loop invariant code motion are 2 other examples. So let's now turn to the flow graph abstraction for reaching definitions. We have a data model that has 2 parts to it: a semi-lattice of subsets of definitions, which we'll call the data flow values, and a directed graph in which each node represents the basic blocks and whose edges indicate which blocks can follow other blocks. And associated with each node of the graph are 2 members of the semi-lattice, one for the beginning and one for the end. There are 2 operations in the flow graph abstraction. One is a transfer function associated with each node of the flow graph. And the transfer function computes the output data flow values associated with the end of the node from the input data flow values associated with the beginning of the node. And then there's a confluence operator that computes the data flow values associated with the beginning of a node from the data flow values at the ends of all the predecessors of that node in the flow graph. And the confluence operator needs to have the properties of a semi-lattice. It needs to be commutative, associative, and idempotent. And for flow graphs, union is the meet operator, the confluence operator for flow graph abstractions for reaching definitions. What's interesting about this abstraction is that there are many different implementations that one can use to solve the data flow values at the beginnings and the ends of the nodes. You create a set of data flow equations, and these equations can be solved with a variety of methods. I like the meet over all predecessors method. You can find the details of these abstractions in a sequence of books that Jeff Ullman and I and some co-authors wrote between 1977 and 2007. The first compiler book was written by Jeff and me, and it had this fanciful cover, which was designed by Jeff Ullman, of a dragon, a ferocious dragon, representing the complexity of compiler design. And then you have this poor compiler implementer armed with a few tools that we had at that time to fight and try to slay the complexity of compiler design. 10 years later, we wrote a second version of the book using Ravi Sethi as a co-author. And then 10 years later, we created another version of the book, adding Monica Lamb of Stanford University as a co-author. I might note that the first compiler book was 600 pages long. The second one was 800 pages long, and the third one was 1,000 pages long. None of us had the heart to write a fourth compiler book. So here's another opportunity to codify all of what's been learned about compilers since 2007. And I suspect it may take more than 200 pages to include the new results in compilation at that time. I might mention that the Red Dragon book, the middle one, was shown in the 1995 movie Hackers that had a young Angelina Jolie in it. My two daughters saw this movie. They had seen the compiler book on our dining room table, but this was the first time they thought their old man was really something. It takes a lot to impress your children these days. But perhaps the most gratifying part to me of these compiler books is the improvements that algorithms and abstractions that they codified have created in compiler design. IBM created the first compiler for a high-level programming language in the mid to late 1950s. It was for Fortran, and it took 18 experienced staff years to create that Fortran compiler. As Tim mentioned, in 1995, I joined Columbia University, and my favorite course to teach there was the Programming Languages and Translators course. And in it, I organized the students into teams of 5, and each team had to design their own innovative new programming language and write a compiler for it. But because of the abstractions and algorithms that were taught in the course, and because of the tools Lex and Yak, and also because of the lightweight software engineering process that I had learned at Bell Labs after spending 30 years there, I'm proud to say that never did a team fail to deliver a working compiler at the end of the semester for the language that they had created at the beginning of the semester. I might also mention that the languages that the students created often far exceeded my expectations. One interesting example of a language they created was a language created by a team that had a former stockbroker as a member of the team. It was a language called Upbeat, where the B was a flat sign. And this language allowed you to sonify data. That is to say, you could write computer programs that would put music, user-specified music, to user-specified patterns in the input stream of data. And to illustrate their language, they took the ticker tape ticker tape flow of the New York Stock Exchange, and they then looked for patterns where the stock market was going up and the music would be lively and bouncy. And when the stock market was going down that day, the music would be dull and gloomy. And the stockbroker who was on the team, he was a little mature student, because I would have never dreamed of this project. He said to me that the last thing you want to do as a stockbroker is spend all day watching the ticker tape. What you could do with the language like this is listen to the music coming out of the stock market or out of this program, and then you have an idea of which way the market was going by listening to the music that was being played. So I thought this was a very innovative programming language and probably a very useful one. I don't know whether any brokerage houses have actually used it. The student is now a professor at Cambridge University in England. Let's turn to a brand new area of computer science. Well, not quite brand new. Quantum computing programming languages. And what I'd like to do is show some of the abstractions that appear in quantum computing that are very unlike the abstractions that we have seen in traditional programming languages. And these abstractions arise from quantum mechanics. Now, as you all know, quantum mechanics is a branch of physics that was developed in the early 1900s to describe the physical properties of nature at the scale of atoms and subatomic particles. And there is a very nice book written by Nielsen Chung. It's the Bible of quantum computing that says everything you need to know about quantum mechanics can be derived from four postulates. So I like to present these four postulates as they appear in Nielsen and Chung. And I've simplified them a little bit to avoid getting into too much complex mathematics. The first postulate states that the state space of an isolated physical system can be modeled by a Hilbert space. And a Hilbert space is just a complex vector space with an inner product. And the state of that isolated physical system can be completely described by a unit vector in the state space. So this looks cool. All you need to know about a quantum mechanical system is its state vector. This postulate also lets us define the fundamental unit in quantum computing, the quantum bit, called a qubit. And a quantum bit can be described by a unit vector in this two-dimensional state space. So here I've shown a two-dimensional vector using Paul Dirac's bracket notation. Those funny brackets are used universally by physicists in quantum mechanics. So they're a very succinct way of representing vectors, and I'm going to use them in my talk. So we have a qubit psi whose state is represented by the linear combination of applying a complex number to the two computational basis vectors of the Hilbert space. Alpha and beta are complex numbers. We pronounce the vector 0 with the brackets around it as ket 0. Ket is the suffix of bracket, which is what Dirac called his notation. And ket 0 represents the vector 1, 0, and ket 1 represents the vector 0, 1. And since we're dealing with a unit vector, the squares of the absolute values of the coefficients sum to 1. And we say that the qubit psi is in a superposition of the states ket 0 and ket 1. Superposition is one of the quintessential properties of quantum mechanics. And a lot of people say you can think of a superposition like a dimmer light switch, that it can be both on and off at the same time, just the same way that the qubit is a linear combination of the two basis states here. The second postulate is how to represent the evolution of the state vector. And one way of viewing the evolution of the state vector of a closed quantum system from one time to another can be described by a unitary operator. And for the purposes of this talk, just think of a unitary operator as a square matrix of complex numbers where the rows and columns are orthonormal. If you want to be fancy, you can say a matrix U is unitary if the matrix multiplied by its conjugate transpose yields the identity matrix. But I like the definition. It's a square matrix where the rows and columns are orthonormal. There is another way of formulating this second postulate using Schrodinger's equation. The physicists love Schrodinger's equation, but I like postulate 2 because this allows us to define the quantum circuit formulation of quantum programming languages. And just to illustrate, the unitary operators can form the gates in our quantum circuit. One very useful operator is the Hadamard operator, which has the matrix representation shown there. And what the Hadamard operator does is it just rotates a unit vector representing the state of a quantum mechanical system. And I've shown what happens to the qubit alpha ket 0 plus beta ket 1 when you apply the Hadamard transform to it. And you'll notice that if we apply the Hadamard transform twice, we get the identity matrix. So you might think of the Hadamard transform as the square root of the identity matrix, but it's simpler to think of it as a rotation of the unit vector in Hilbert space. Another useful unitary transform is the 2-qubit controlled knot quantum operator. It's often called the C-knot operator. And it has the matrix representation I've shown on this slide. You'll notice that the rows and columns of this matrix are orthonormal. So this is a unitary matrix. And what the C-knot gate does is it flips the target qubit of a C-knot gate. A C-knot gate has 2 wires coming in, a control wire C and a target wire T. And if the control wire has the value 1, it flips the value of the target qubit. Otherwise, it lets the target qubit go through without change. That's exclusive OR on C, exclusive OR T on the output of the second line. And if we look at the behavior of the C-knot gate, we see that if the input consists of the qubit, the two qubits, 0, 0, the tensor product of the 2 qubits, ket 0, ket 0, it maps 0, 0 to 0, 0 and 0, 1 to 0, 1, not changing the target qubit. But if the control qubit has a value 1, then it changes the target qubit from a 0 to 1, as shown in the second line there. And I'll talk about tensor products shortly. The third postulate of quantum mechanics is measurement. And if we want to get any information from a closed quantum system, we need to apply measurements to it. A measurement returns an outcome with some probability, and the sum of the probabilities of the possible outcomes is 1. And measurements have the property that they collapse part of the state of a quantum system. So let's just take a simple example of measuring a single qubit with a projective measurement. So let's take the single qubit psi, which is the linear combination of the basis states 0 and 1, and we apply a projective measurement to it. What the projective measurement does is it collapses the superposition either into the state ket 0 or the state ket 1. And if the measurement collapses the state to ket 0, it produces as output the classical bit 0. And if it collapses the state to ket 1, it produces the classical bit 1. So what a measurement gate does, it takes a qubit as input and produces as output a classical bit. This is a very strong limitation on quantum computing because we can't get at the amplitudes alpha and beta directly. All we can do is get a classical bit as the output of a measurement. Postulate 4 says that if we combine 2 isolated physical systems, the state of the composite physical system is the tensor product of the state spaces of its component subsystems. So here I've shown that if we have three two-dimensional vectors, A, B, and C, if we take the tensor product of A and B, we get a four-dimensional state vector. And if we take the tensor product of the three basis vectors, we get a eight-dimensional state vector. So if we have n single qubit isolated physical systems and we combine them, we end up with a combined system that has a state space of dimension 2 to the n. And as John Martinez mentioned in his brilliant keynote talk yesterday, if we combine 300 qubits, we get a state space that has a dimension that's greater than the number of atoms in the known universe. So this is just reiterating what I said. If we combine n single qubit systems, we get a state space of dimension 2 to the n. And now we're ready to define quantum circuits, one of the fundamental abstractions for quantum systems. And a quantum circuit is like a Boolean circuit, but there are some major differences. A quantum circuit is an acyclic graph. It has lines, quantum gates, and measurement gates, but there are some restrictions. You can't have fan-in because the logical OR operator is not a unitary operator. You can't have fan-out because in quantum mechanics, there's something called the no-cloning theorem, which states that it is not possible to make a copy of unknown quantum state. But here is a very simple example of a quantum circuit. You see it has two lines, X and Y, coming in, and it has two lines coming out. The X line is connected to a Hadamard gate, and the output of the Hadamard gate is connected to the control wire of a C0 gate, and the Y wire is connected as the target wire of the C0 gate. And when we apply the Hadamard gate and the C0 gate, we generate some very interesting output states, which are called EPR states. Sometimes they're also called Bell states. And these states have the property that they're entangled states, that you cannot write the state as a tensor product of two basis states. Einstein called this aspect of quantum mechanics spooky action at a distance. Many people believe that entanglement is what gives quantum computing its great potential power, but entanglement is still a mystery to physicists. It's certainly a mystery to me, but enough said. I'd just like to conclude by saying that in 1994, Peter Shor, who was at Bell Labs at the time, gave a hybrid classical computer, quantum computer algorithm for factoring an n-bit integer in a polynomial number of operations in basically order n cubed time or order n skewed log n, log n operations. All of the known deterministic algorithms on classical computers for factoring integers run in more than polynomial time. So this had a big shock to particularly to the encryption community, because the encryption scheme RSA assumed that it was computationally infeasible to factor large integers. But Shor's results said that if we can build a big enough quantum computer, then the RSA can be cracked very easily. But as John Martinez said, we're far from the point in time where we can construct quantum computers big enough to be able to implement Shor's algorithm. And what I'd like to just conclude with is that the bedrock framework that we presented for compiling programming languages can also apply to quantum computing programming languages. And 20 years ago, I had a PhD student who came to Columbia from Princeton to study quantum computing. She took my programming languages and translators course and fell in love with programming languages and compilers. And then she showed that you could adapt our compiling framework to apply to quantum programming languages, putting in fault tolerance and quantum error correcting codes into the design flow. And after graduating, she went to Microsoft Research, where she is now the general manager of quantum software. And a few years ago, she and her colleagues developed a quantum programming language called Q#, which is now part of the quantum development kit that Microsoft has put into the Visual Studio. Her name is Krista Sforey, and you'll see her giving a lot of lectures on the potential of quantum programming, quantum computing. But what we're still waiting for are John Martinez and company to be able to build the very large million plus qubit quantum computers that are required to run Shor's algorithm with error correction. So I'd like to just conclude by saying that abstractions and algorithms have transformed the field of compiler design from an art to a science. And I'm sure all of you could make a similar statement that abstractions and algorithms have transformed computer science into a true field of science. Thank you.